This is where we stopped last time, and I would like to discuss a few more models of exception handling and interrupt handling. I would like to enable you to design a new environment, a new programming language, and you should take a reference of what previous languages have been doing so far and what they're doing wrong, what you can do better. For completion, 3 different modes of exception recovery processing. And exception recovery is not something you can wing in post. If the programming language and the compiler doesn't give you a specific feature, you have almost no possibility to repair this in post. Resumption model. Resumption means that if you have an exception, you handle it, you continue in the same spot as if nothing happened. This is just like an interrupt, so to speak. Your normal program flow triggers an interrupt, something else happens, and you continue at the same spot. And Perl is one of the very traditional old processing real-time control languages actually offer that as an option, not as an only possibility, because in a real-time language as an only possibility, of course, you would be shooting yourself in the foot if you don't have a possibility to actually get out of something. That's the Eiffel interpretation of exception recovery, block resumption, that you insist that contracts are never being broken. So if anything goes wrong while a contract is attempted to be fulfilled, go back to the beginning, try again until you actually finally get out of this or not. Not necessary to mention that Eiffel is not exactly a real-time programming language. Or termination, which is the only model in most real-time environments, or it is at least offered in all real-time environments. In most real-time environments, you only have this one. Issue, you have no way to continue after an exception has been raised. You only can go back and recall the same thing again by hand, manually, but you cannot just continue as if nothing happens. What would you wish for your new designed, brand new, all-solving real-time programming language? Okay, I shall be patient, waiting until you publish your new real-time programming language. Maybe you go for the hybrid model. You give your programmer a choice. You can attribute your exceptions or your exception handler what you want to do after the exception has been handled. Or is the runtime overhead too much for it? Okay. Would you embed this in your programming language, that you can re-raise an exception multiple times? You have probably been doing this in your programming so far, handling exception a little bit, but there's still stuff to do, and you still press the supervisory button, next step up. I've done my bit, now the next level up has to repair as well, etc., etc. You can re-raise exceptions.
Does that involve an undefined stack? Like, is that bad? Like, because you can't have recursion in like a previous is that the sort of problem that you could have here? Stack.
That's a good question. You actually catch it multiple times with the same handler if you have recursion here. Is that a problem?
The craving scale doesn't allow it, I guess that means that.
That's why I'm asking. Craving scale doesn't allow it. It's simply back forward.
Well, it's certainly a complication that you put it like that. But it's I leave it up to you to decide how bad it really is. Whether you want that or you want to have the exception handling facilities more simplified. You will kill the erasing possibilities.
What is ASA? Like, what is Raven's
Raven's is to say that, because grading scale says that. Maybe you want to have something different. Okay. A few issues I would like to throw at you in terms of exception handling. Where do we declare exceptions? And Ada is particularly bad in that, because it's often very hard to find what can actually raise an exception. If you do it very fine-grained, then you have to attribute your exception at every little function which can raise an exception. If you do it very coarse-grained, you don't find where the exception comes from. I'm calling this a set of functions in my interface. Can I expect an exception to happen or not? Maybe that's not clear, because you declare your exceptions on package level. And maybe only one of the functions inside your package will ever raise this exception. If you have to read the implementation to find that out, a little troublesome. So that's not quite clear, and I think Ada is not doing a fantastic job in that one. Next one is equally problematic for all strongly typed, strongly scoped programming languages like Ada. You can re-raise exceptions, you can propagate exceptions. You have your exception visible where you declare the method which can call them. So whenever you have directly access to calling this function, you can raise this exception. Of course, I know what the name of the exception is because it's on the same level. But if I re-raise exceptions, or I don't have an exception handler in the first place, it just whizzes past. Whizzes upstairs, so to speak. The upstairs, at some point, has no visibility to this local scope anymore. Let's put it to the extreme. You have one exception handler in the outermost scope of your whole system. Most likely, this outermost exception handler doesn't know a single name of your exceptions anyway. Because in order to have all of these in a scope language, you would need to be importing every little module throughout the whole thing. Or you have my all flat, so that I have no hierarchy, everything is on the same level. C approach. There is no scope. That problem. Because everything is visible because everything is on the same level anyway. But if you have a scope language, it's quite clear. And one of the charms of exception handling is, of course, you can handle exceptions which are happening 25 levels below you. But the data structures which have been defined, all the interfaces which have been defined 25 levels below you, are not in the scope. These are the names of the exceptions. So yes, you do find occasionally anonymous with other handlers in Ada programs. This is actually not visible.
If you have your hierarchy if I understand, why are the names not in the scope? They're underneath you. Don't you have access, so to speak, to everything below?
If this has been imported locally as a generic module somewhere down there, as it all happens, it's just a local import.
But then it's how hierarchies work. It's valid for them, which is valid for the path. So if one for someone,
Not for all. No, not for all. Like, yeah, that would mean that you have full visibility of every detail. There's no local scoping anymore. You cannot access local variables, in my opinion. You're looking at scoping the wrong way around. From the innermost level, I can go outside. I cannot go parallel on the same scope level. I can just go straight outside. The other way that doesn't work. I can do into my local variable scopes.
Would it potentially work that at whatever the top level language, any amount of exception handling is still existed? You basically had a table of exceptions that could be added to by packages, as packages are instantiated further down.
That would be a possibility that you handle exception names differently from your local visibility rules. There are different visibility rules for exceptions.
I think you can make an exception for exceptions.
Okay.
Like in Ada, you seem to do this by making a package explicitly for exceptions. Is that not a simple solution?
Yeah, well, that's convention. one convention. Unfortunately, you do find practical data codes in situations where exceptions are propagated outside of this scope. Because that means that everybody agrees on this one central exception handling module. If you have a whole bunch of programmers and different companies involved, that's not necessarily the case. The next one is not so bad, but it's usually perceived really bad by beginners, by people working for a long time that feel that's not really perceived a problem, that exceptions in task bodies are not propagated apparent. So if you crash inside the body of a task and you don't find an exception handler there, the task dies out. This is actually welcome rather than considered a problem in most cases. That means if this guy hasn't really done his homework, no exception handler whatsoever, just let him take it. Don't kick out the rest of the system. But if you, the inverse would be true. If you always raise an exception there, it would mean that you possibly raise exceptions which the parent is almost unable, utterly unable to handle.
If you've got a task and it launches a subtask, and that subtask raises an exception and doesn't handle it correctly, so it dies silently. Yeah. If the parent task reaches the end of their task body, will it terminate?
Yes, it will. From the perspective of the parent task, it looks like normal domination.
Wouldn't the parent task want to know that the child has died, even if you have a default behavior to do nothing? At least have the option. It could be really important that that little child stop doing its thing.
The problem is, from the perspective of the parent, it is not any different from the task doing normal termination. Because it actually, you propagate all the way out and you reach the end statement of the task. Going over the end statement of the task is a synonym with termination of the whole thing. I see what you're trying to get at. That it's a different form of termination. And how do you want to communicate this with the parent task?
Isn't that what exception handlers are for?
Now, the problem is, this exception, when does this exception occur?
When the child task runs into the problem at some point?
Yes, and from the perspective of the parent task, when is this?
Just sometime after it starts it.
Yes, anytime. So from the perspective of the parent task, this is asynchronous. And all exception handling, what we have done here, is strictly synchronous. The concept of handling asynchronous exceptions, we will have to discuss in a moment here. But so far, you may be opening a door to hell if you allow exceptions to describe asynchronously. Or concretely, your parent task has 25 different exception handlers for all different purposes and environments. Now, your child task raises an exception which is hitting any of these 25 exception handlers at random, because your parent task can be any possible state at this time. Which means that all your 25 exception handlers need to be prepared to handle this one exception from the child task in all different contexts and environments. Ooh, a little scared.
Could you effectively set some kind of variable that would be available once that task has died, such that, I guess, the
global variable approach is also not very.
Well, but not necessarily but just in the parent task, wherever it's storing that reference to the subtask, also just add an extra thing there. So basically, I guess the metaphor would be so that when it goes to check the body of the subtask, it says, oh, it died of natural causes versus it was murdered.
Yeah. But for that, in that context, this is so easy to program by hand. This is a two-liner. You have a catch-all exception handler in your child task, which sets this whatever value you want here in your parent task and done.
Alternatively, you could have like the last line of your child task, just send a message back to your parent saying that I'm done.
Yeah, or you explicitly synchronize that if the synchronization never reached me. I assumed that the guy must have been killed in unpleasant ways. And or actively falling back that if I got in trouble because I had an unfold acceptance on place, I have practice with my time class. But it's so easy that in a professional environment, you wouldn't consider this making this part of mandatory language design. Because if you need that, at least 2 lines to your time class. Exceptions in task declarations are always propagated with parent tasks. That's true in underlying entity. Is that a good idea? You understand what that means?
Should exceptions in the task declaration be revealed at compile time?
Or it could be, for example, memory allocation. Try to allocate your child task and you run out of memory, and then your child task goes, I'm half-baked, I just need to like pressure. Or I'm not starting. Exactly in that way.
So this is still happening synchronously, right?
Yes, that's the point. That's harmless because this exception is actually a synchronous exception. It happens during the declaration phase of the task, and the parent task has a very clear idea when it exists. So the parent task has not yet reached actual execution yet. It goes through the declaration part, and the declaration part itself crashes. From the perspective of the parent task, it's like you try to allocate, for example, a large array, and you run out of memory. That exception which you get from that is also a synchronous exception. It's not different from allocating a large array or allocating a task.
When I use the that you can't send exception or the parent task can't know if the child died of that exception, is there anything enable that interrupt when if the child dies of exception and then that lets it know to the parent task that it did not die of normal causes?
Well, we just said this is very easy to program manually, and without any interrupts you can do this completely synchronously. Well, if you really want to do this asynchronously, we can come back later for asynchronous controllers. Yes, I wouldn't take this gun out for that kind of purpose, but theoretically we can. Last one is if you are in a rendezvous and both tasks are synchronized at this point, if the receiving task is coming to any kind of exception situation, then this exception is raised on both ends at the same time. Maybe a little confusing that you have one reason, which is trigger something, and you have 2 exception parties starting your 2 different tasks at the same time. Concurrent exception handling, so to speak. Maybe a little bit problematic. I don't think it's actually that problematic.
How does the Hushan cause and that info? Does it allow you to have the same exception like handler or like similar thing to handler?
Yes. Well, if it's happening during the handing over of the message, once the client is relieved and the server is running, then of course the client will never get this exception. But only if it happens during handing over of the message, then both are being activated. And it's important to understand these details between different forms of exception handling in concurrent environments when which task is being alerted to that situation. And when it's not alerted at all.
Just double checking. So if you go on your receiving end, you have accept entry E, and then you have a raise exception and then end select or end except whatever it is, right? Is that raise exception raised in both of them?
Yes.
But if you did that outside of the whatever it is.
What about excepts inside of other excepts? So that I got kind of read on 2 tasks synchronized.
Yes,
All
that
3 tasks.
depends how you handle it on the receiving side. If you don't handle it, you can handle it in the scope of the second internal accept. Then you stop it before it actually triggers an exception in the outside exception. So both things can happen here. You can actually then trigger a cascade of accepting all 3 tasks, or you can limit it by catching it directly on the spot, on the server side. And as we discussed last time, some of these exception problems are expensive. Any further questions about different possibilities to do exception handling? Are you wishing now that languages are abandoning exception handling? As some languages decide, do you wish for better exception handling? What is your favorite exception handling facility so far? What languages do you enjoy exception handling in?
Python stack trace to be one of the nicest to read through. I was rather stumped yesterday when during operating system boot up I got a problem with Python stack trace, but apart from that, it's one of the better ones to read through.
Okay.
It's great JavaScript library which runs your code. Then it has an on-code error. So it hits that line and runs it again.
Well, it's still better than the other more classical JavaScript approach that if you have an error, just keep going. I hope you can enjoy good debugging environments and good stack traces in your languages. Having good support for that is quite essential. The stack trace, which you can get from Ada environments, depends very much on the runtime environment, the operating system. Quite frustratingly, Mac users are always being bitten in that one because GNAT is not really providing any decent stack trace on Macs, but they do provide decent stack traces on Windows and Linux. Or we go object-oriented. Exception handling is, of course, inherited from throwable. It can be an exception or can be an error, and some of the exceptions are interrupted exceptions, and some of the interrupt exceptions are asynchronously interrupted exceptions. And there is hierarchy and inheritance to the whole thing. There's some beauty to it, if I can make this part of a larger story. How efficient that is, or whether you gain something in terms of structure of your program. Let's look at it into more detail. The advantage is you have now one more possibility than what you have if you only have a flat namespace for exceptions. You can catch an individual one, you can catch one out of a list of exceptions, or you can now catch a class of exceptions. That's something you cannot do in Ada. Yes, Ada is object-oriented, yeah, but not when it comes to exception handling. Exception handling is just plain flat. Or you, of course, have a catch-all one. Now, this is giving you the most flexibility in terms of exception handler writing. Nice. That's a short story. Exception handling in C and POSIX. If you need to do that, welcome to the nightmare of global variables and long jumps and things like that. So there is just no exception handling. We all wish there would be some, but there isn't. Summary of exception handlers which you have seen so far in the lecture. And they're differentiating particularly in where you declare exceptions, what happens after recovery, and whether you can declare this just as a name associated directly with a handler. That means there's no propagation. Or you can declare this as a whole class. Remind me, do you declare exceptions in Python also as a class? Python fans? You can, or it's by default a class? Okay. Cool. So, before we implement interrupts and further details on those asynchronous exceptions, I would like to go back to the atomic actions which were already implemented there. First, do you have any questions about the atomic actions which were implemented in the labs? Was that reasonably easy and straightforward? Atomic actions are an essential part of high integrity programming. Hence, I'm rubbing that a little bit. You have different commitment types. You can join in a number of concurrent entities into the whole thing. It's basically atomicity on a much, much larger level. Those who are experienced in database systems, you will be reminded of transaction protocols. That's quite similar to that. This is a more general concept. Transaction protocols are still centralized to a specific database. This can be concurrent and running everywhere in your system in a distributed way. Can you nest atomic actions? Sure. If it's a true subset, fine. What does that mean in practice? We have nested atomic actions like that. Let's first look at what do we need for real-time environments. Clear starting points. So we need to relate this now to timing relations as well. Nesting is fine. And it gives you a much, much easier play at concurrency in real-time systems if you have large-scale atomic operations, because you do know they are atomic operations, so they can be executed completely concurrently. So you have a very easy way of designing highly concurrent systems without needing to mess with further communication. Easy. What happens if one of these tasks fails in an atomic action?
You basically roll back the changes that were made. Otherwise,
Yeah. The tricky part is if this is an atomic operation on that scale, that means you have multiple processes involved in one atomic operation. That means you have to be able to signal to all the other processes that you have to roll back. That makes it a much more complicated and cumbersome operation. What happens if you have nested operations and they're crashing? Nesting atomic actions. The outer atomic operation, in this case, crashed before the inner operation is complete. Can you talk to the inner atomic operation? Okay. Say again?
You have to wait for the inner one to finish or fail, and then abort anyway.
You could include whatever's monitoring the outer task as part of the atomic action of the inner, so as part of the joining task of the inner atomic action.
No, a task cannot be joining multiple atomic operations at the same time. You are leaving the scope of the outer.
So the inner one is still complete because it has to stop.
Yes. Yes. It's just annoying sitting at the sidelines, knowing that the world is going to shift. And this inner atomic action is happily clicking along. And you know that you only have to wait until the kids which actually happily play along are finished to tell them, this is all in vain, go back to start.
Like in the way we implement it in data. So there's a monitor where we kind of have ourselves once we onboard, like when the monitor is part of the user board. Can the object has kind of modify the monitor according to
Yeah, well, I'm breaking the concept of atomic operations if I do that.
we're not changing the task, but just modify the monitor.
you have so your outer atomic option is a real hard time deadline, right? It must complete in 5 seconds, but the inner one doesn't have such a deadline.
Yeah, that's a design flaw if you actually do it like that.
Well, does that mean that you have to make you have to propagate your sort of deadlines?
Yes, of course. If you have to guarantee an outer deadline, you already have taken the worst case calculations for all of your components anyway, which includes the inner atomic operation. So you know that you can make your outer deadline, even if the inner atomic operation is really, really slow.
Yeah, but normally that would be like you would. So for other things, you can interrupt your own atomic operation.
Yeah, unless we're breaking it. So in this case, you break atomicity and inform the inner atomic operation straight away.
Would you want to do that for any reason besides efficiency?
Yeah, that's a good point, and it refers to the previous question as well. What do you actually gain from it? You're gaining more resources for your system because you stop execution unnecessary. You stop unnecessary execution. You need to gain a little bit more CPU power back for the overall system. So you can look at it from two different perspectives. Gaining additional CPU power for your overall system can potentially enhance redundancy in the system. You can also look at it from the perspective of this is a hard real-time system, and know that I will fulfill my promises even if everybody is at the slowest possible pace. And from that perspective, I would probably choose the former option. I'm not breaking atomicity. I know that I can handle the worst case, so don't stop it. In the other consideration, I say I really want to have additional resources if I can afford them. I can reclaim resources, for example, CPU resource. I would possibly consider doing that. So I can argue in both ways in a hard real-time system. Okay. What happens if the inner atomic operation fails?
And the outer operation can handle that better. It doesn't necessarily get better.
It's similar, but a little different. It could mean that the outer operation can still complete because it doesn't rely on that information. And propagating something to the outside is still a different story than propagating something to an enclosed inner scope. If I propagate a failure into an inner scope, it may be more acceptable in some circumstances than propagating exception to an outer scope when I do that. Tricky in both cases. Here's what you have been trying to do, define atomic operations like that, atomic operations with these number of processes. Just do it, and if an exception happens, raise one of them. Very nice. Doesn't exist. There's no programming language which would allow you to formulate anything like that. This level of atomicity is not supported anywhere. But what we can do if you have asynchronous transfer of control possibilities is what you have been programming here. Defining data structures which define your atomic operation, and then have a perform routine which takes this data structure and executes all of this code in a distributed way as an atomic operation. What was the structure you do with that? Do you remember your code from the lab exercises for that, I guess? The first thing you do, you have now a whole cascade of select and abort selections. The first select and abort is you leave your business card The idea is that the fail is blocked by default, and the fail call is not going through. Just leaving my business card there in case this call would ever go through, then I will fall into that one and abort everything else. It's just a reminder for me, if my atomic operation is ever declared fails, I have to do something else. I have to abort everything which I'm doing. The idea is you're not actually going there, you're executing your atomic operation normally. This is only if something fails. The next one, select delay, then abort another delay. But confusing, these two delays have a very different semantic meaning. The normal path is to be found in the abortable part again. So the normal execution path here is you delay for your minimum delay in your atomic operation. You explicitly suspend your task for the minimum delay. If you're coming out of your minimum delay, clean, nothing else happened, what else could have happened? You have been oversleeping. So your task has been put to sleep, but it did not wake up until the maximum delay has been passing. If the maximum delay has been passing, then you abort that and raise an exception.
Couldn't you just check the current clock time after you come out of the delay?
Yes. Yes. This is more dependable because here I leave it completely to scheduler. If you do it in your normal processing and you check the clock by hand, it means that you're subject to the actual, whether you actually need scheduled. You have to execute code. And this can be, you have a context switch here at any point in time. So even your task has been activated in time, it's all good, but it didn't get enough CPU time to actually look at the wall clock to find out whether the maximum delay has been triggered. So this is safer to do it like that. But it's more complicated, I think. So you can have balance between, I want to have a simpler design, which is a little bit softer, but much easier to read than that. Fair enough. And finally, we have the actual deadline. Next select and abort statement. And if this deadline is violated, we again can raise an exception. All these exceptions are ending in this exception handler block, which is still inside the abortable part. Please take note, this is inside the outside select statement. Which means the outside select statement is still active even though we have one exception handling. The outside select statement was the one which made us wait on the failure call to go through. And that means we can do something pretty tricky. We can handle this exception, call actively to the central monitor to inform everybody else, and starting by informing the monitor that our atomic action is a failure. We failed for one of those reasons. And the interesting part is, even though this task here already knows, but it actually follows the same pattern as all the other tasks, it leaves this exception handler. What happens next? It's actually not getting out of the exception handler. Because while it's trying to get out of this exception handler, the outer select statement is now triggered. Because the outer select statement has now the failure opened. Which means this task is declaring failure and falling also itself into the failure processing on the outside. Which means I don't have to replicate the code for resumption. And so let's go back to the outside again. And the cleanup task, which have to be done by this task, is still done as if somebody else would have raised this failure. I've raised this failure, I'm ending here. Somebody else raised this failure, I'm ending exactly the same spot as well.
Do you get any benefit from using exceptions instead of inlining them?
Inlining them?
So each exception raised for a specific monitor fail or thing.
Yes.
Would just replace them with raise blah blah blah.
Yes, the advantage is that I need to have an exception handler anyway, because I need quite desperately the exception others in this context here. There could be a lot of stuff happening in this atomic action, in the performance atomic action. And this is a bit easier to read, but you're right. Instead of raising it up, raising this exception up there, I could. No, I could not actually. No, that would be wrong. Because if I would be handling this here manually, I would continue after this select statement and I would actually call the monitor tracker. The advantage which I get by doing all of this by exception handling is that I automatically skip all the rest of the processing, including quite vitally the monitor tracker.
It wouldn't need to go run the test.
Yeah.
The gap would be active.
Yeah, you're right. Yes, I would actually be getting out of this. Yeah, you're right. Okay, take it back. Good work. And that's boring. The monitor is actually quite simplistic. The only thing you need to notice here that they are all entries, which can be open and closed under different circumstances. Okay, easy enough. Now, if something goes bad in those environments, what do you do in a real-time environment if something goes bad?
Very general question.
It is.
Change the name group so that no extradition tree.
Yeah. What do you do in a, say, database environment if something happens inside your database? You're trying to roll back. You're trying to undo what you have done so far. So I know I'm in trouble. I'm not getting to this point. I can run two different strategies. I can try a different strategy to get to my transaction exit point, or I can give in and say that I'm rolling back to the beginning. So I couldn't do it, but I also didn't destroy my database in the process. Right? Is that the classical real-time programming approach? So no, I couldn't actually land the plane, but I brought all the on-board electronic systems back to the initial state, so I'm fine, right? Can you even do that? Even if you wanted to? Why can't you do this in a database system? You will run a transaction log, it's kind of journal in the whole operation. You will store a lot of information along the lines, which enables you to roll back in a real-time system. Yeah. You usually think a lot more physical. Now, you drove over the cliff. Undo, undo. In a database system, that's easy, usually. Or it can be done. if a database system is not seriously addressing that, it's not a database. But in the physical system, most of the things you're doing are undoable. You have to just live with that. Which means that backward error recovery in a real-time system is actually quite rare. What's your plan? What does that mean for this forward error recovery? Keep trying. Well, that's not exactly forward. Keep trying.
You decide beforehand that it is possible that this will fail. Here is how we'll do it.
Yeah.
And then do that.
Yeah. So, yeah.
I think this conversation is too general. Like, he's asking such a broad question and expecting an answer.
Getting lots of answers.
But they're all like, just do whatever is the right thing to do at the time.
No, not quite. Not quite. I think the strategy which we're getting at is you usually have some form of a mode change in a real-time system. That you have an error which you want to recover from, but instead of getting everything to a honky-dory, everything is fine state, you accept that you now have been breaking away some part of your functionality. Something failed, something is no longer available. And you try to make your system survive based on a lower level of functionality. You go to a different mode, survival mode. You go to a lower functionality mode. You go to a mode which enables safe landing, but the comfort may be reduced. Right? So you go to the mode where you save all the power in your plane by powering down your onboard entertainment system and killing a lot of functionality which is unnecessary at the moment, but you focus at a few things which are actually mandatory. Still too generic?
That's for one system though. Like, some things are recoverable and they're real time. They're not a conflict, are they?
Well, I still would make the point that if you have a physical interacting system, then most of these systems, of course it's a generalization, but most of these systems will have unrecoverable components to them.
Would that be basically the equivalent of like operating system setting words, where often if the operating system isn't able to boot for whatever reason, it'll attempt to boot into this like really limited,
Yeah.
bare bones.
Yeah, yeah. That's a nice equivalent to that one. Even though it has nothing to do with real-time systems in that case, but this is also a case of forward error recovery. I actually don't have this resource. This device doesn't respond. I have to find some other way to survive. Okay, next level of decision, interrupts or asynchronous transfer of control. Asynchronous transfer of control is frequently employed in the context of mode changes. Change to a completely different behavior in your tasking. Interrupts are more direct and used in normal part of your processing. Asynchronous transfer of control can or cannot be used in normal part of operation. Asynchronous events. In real-time Java, we have a number of very simple things. You can have asynchronous events which are bound directly to a handler. This is similar to an interrupt handler, but it's more general, because asynchronous events can be coming from anywhere, including other tasks. That's different from an actual interrupt handler, which is more based on physical operations and physical interrupts. Real-time Java has these asynchronous events which are also handled as a schedulable object. So they are not handled on the level of interrupt handlers. The downside of that is more flexible, but it's less direct, less immediate what you can do there. Okay, that's not really essential. I would like to skip over that stuff. Exception handling is important though. And now I'm coming back to, do you want to have asynchronous exceptions? Java is offering something which is called an interrupted exception. Interrupt exception sounds pretty asynchronous. But don't be fooled by the name. That's still standard Java, that's not real-time Java. There is no asynchronous effect here at all. I was a bit annoyed by choosing the completely wrong terminology here, because this has definitely nothing to do with interrupts. What we actually have in Java as interrupted exceptions is the process which has received an interrupted exception to call whether this is the case or not. This process has to call whether this is the case or not. This is not really interrupted. This is just setting the old flag which we call active. Okay, so that's something they realized in real-time Java and expanded on that in the classical Java way. So we have now an asynchronously interrupted exception. Names grow a little bit. And then now make the point that it's not just an interrupt which is called interrupt, but it's a serious interrupt, it's an asynchronous interrupt. And that triggers all kinds of complications. Asynchronous interrupt exception. A number of things are not interruptible. Fine. But what actually happens if such an asynchronous interrupted exception strikes? How do you handle this from the perspective of an individual process? Okay, a number of things which come automatically from that. If you're in a synchronized section, make it wait for a little. Fair enough. If this is an interruptible section, then find the closest dynamically enclosing exception handler. Which one will that be? Dynamically enclosing, that means wherever you currently run with your code, you look at the dynamic call chain on your stack, what is your closest exception handler from this point in your process? And the point is that this spot in your process is very hard to control a priori because this is asynchronous. In your process, as we said previously in the discussion about child tasks and parent tasks creating exceptions, that is exactly what you have in your hands here. That the task, in this case, not the parent or child task, but the task in general, has to now handle exceptions in all of its exception handlers because you cannot predict where this is going to strike. Hence, it's an asynchronous interrupted exception. If the process is sleeping, you kick it alive. If control is in non-interruptible section, you keep waiting until you reach an interruptible section. Fine. And now it becomes weird. If a current exception handling facility is running, an exception is currently half executed and re-raised and propagated somewhere else, and then you have an asynchronous interrupted exception, you replace this normal exception with the asynchronous exception and keep propagating.
Would you replace an asynchronous exception with another asynchronous exception?
It is, and I thought this was complicated enough, and now you get it the next layer. What happens if, depends how your properties are being handled. If all your asynchronous interrupted exceptions are on the same property level, which I would strongly assume, this cannot happen in the first place. Because while you are handling the asynchronous interrupted exception, I'm going wrong name. No other asynchronous exception can happen. So if that's not the case, I'm not sure I want to know. Interesting. This is how this is implemented as different classes, but that's not important. This is important here. You catch an asynchronous interrupted exception by calling stop now. I'm trying to catch this exception, and I can handle it by calling actively stop now. Different from the normal exception handling facility, where you don't have to stop an exception. You handle it, and it's automatically stopped by that. If I'm only responding to this asynchronous exception without calling stop now, my exception is automatically propagated further, even though I did already handle it. Why? That means that everywhere where you have an exception handler, which doesn't really know what to do with that, it may be doing a catch-all, which includes this exception, but it's not really catching it. It's not really stopping it. Because otherwise you need to go through all of your Java libraries, up and down, left, right, back and forth, and amend all the exception handlers which you find across all your Java libraries with the facility to handle this exception. This is not feasible. So what you do instead is you say that this exception is very hard to stop. You actually have to actively stop that one. Otherwise it's just slipping past until it finds an outer exception handler someplace. And that enables you to have a single outer scope exception handler which can handle that. Everything else slips past. Does that make some sense? Is that the exception handling facility you want? Complicated enough? Would you wish for Ada to have something like that as well? Okay. So people have been looking at this hard and sharp for quite a long time, whether it's a good idea to have these asynchronous effects in the same syntactical scope as everything else. This is asynchronous transfer of control, and you do have timeouts on actions in real-time Java. The only reason why you have these interruptible interfaces is because you need as a parameter for the timeout on action operation. This is the select, delay, then abort version, which is an asynchronous transfer of control statement. And this is what you have in real-time Java. You don't have more complex operations like calling on an entry and have then a select and abort. This is what you cannot implement that easily in Java. Or you have a timeout on an operation in that kind of environment. So, and to make life easy again, what do you have in Ada? A whole range of different things. Not everything is an exception in Ada. You have exception handling, which is only synchronous. You have asynchronous transfer of control, which is asynchronous operations between tasks. And you have task aborts, Maybe you don't need them, but you do have them. And you have actual interrupt handling. Cleaner, easier? Or you want to go back to Java? I see we have a split on that. This is the interrupt handler interface. Most of this is not available to you. Why? On your board, it's not available. Yeah.
Is that because a lot of the interrupts are already being used by?
No. That's always the case. Interrupts are used by
No operating systems are marketed.
No, that's not the reason. The reason is that in Radiostar, it is simply forbidden to have dynamic interrupt handlers. And this whole thing is designed to assign a handler to a specific interrupt and then reassign another handler later on time. Flexibility of having multiple interrupt handlers to a specific hardware interrupt. This is considered very bad from a certification perspective. It's much easier to certify code, which is more following a structure of combinatoric logic. And you have certain ping on the input side triggers a certain effect on the output side, but this means you have static allocation. You cannot randomly or dynamically allocate the interrupt handlers for that. Your parameter's interrupt handler has to be a protected procedure. You will see why this is of advantage to have interrupt handlers as protected procedures. Protected objects have priorities. They have implicit priorities. These implicit priorities, the priority ceiling of a protected object, is defined by the highest priority of every component and element which can syntactically access this protected object. So you have tasks on different priorities. All of these tasks can syntactically access this protected object, which means that the priority of the protected object itself is the maximum of all of these priorities. Trust me, you will need that later, that priority for the protected object. And here, you have another priority at play. Because by making this protected procedure part of an exception, part of interrupt handler, means that that specific interrupt has a priority associated with it. And the protected object now has actually a priority which is higher than any of the task priorities. This protected object has now an interrupt level priority, depending on where this interrupt level is, but it's always higher than your task priorities. This will be interesting later on in your calculations about scheduling. You know that this protected object, which has been involved in interrupt handling, is on a much higher priority level than all the other protected objects which you have around. So your resource management is different here. That also means that any task which is ever touching this protected object will run while it's in this protected object on a very, very high priority level, usually overriding all the other task priorities while it's touching this protected object, which is a good idea, because then this task runs on the highest interrupt priority level, which means that the interrupt is disabled automatically while this task touches this object. Cool. So you can exchange information with an interrupt handler in a very simple and safe way. The interrupt handler has implicitly a very high priority. You touch that, your interrupt is automatically disabled. Cool. Whether this actually qualifies as an interrupt handler, you will be told by the compiler. Not everything is allowed from inside the interrupt handler. And if you try to do too fancy things, your compiler will, of course, reject this as an exception, as an interrupt handler. Instead of having a procedure attached handler, what you do in real-time systems and in your specific system, in the slightly more older syntax, you use a pragma. So you define your protected procedure, and then you have a pragma after that. This is associated with this interrupt handler. The current syntax which is used is you have an attribute instead of that. I found that much easier and much smoother to read. You have a procedure which doesn't quite end in this declaration yet. You continue with a number of parameters, which is, for example, its priority, its resource management, memory management, and here also you attach explicitly an interrupt handler. This is, by the way, exactly what you saw in the code earlier today in the slides. It's exactly what you are doing in your practical coding. Cool. You have to guarantee that the Ada language specifications require that if you use any of those things, this means that the actual address of your protected procedure will be directly written in the vector interrupt handler, in your vector table of your machine that you see here. There's no intermediate interpretation level in between. That also means that the number of CPU cycles which it takes between this interrupt happening and you gaining control in your protected procedure is strictly round, minus interrupt property masking. Okay. That's pretty cool. Has to be documented. And it does, in fact, on your machine directly write onto that one. There's a nasty one. Here, Ada breaks types in any imaginable way. Reference system address. This is as low level as it gets. And you actually can ask Ada to tell you the address in your interrupt vector table where this is being stored. Why on earth would that ever be relevant? Well, if you really want to, you can do very nasty stuff there. And you can put any function which is not safe, which is not protected, which is not known into this interrupt handler forced by hand because you do know the system address of your interrupt vector table, of this specific entry in your interrupt vector table. So that's very low level. I was a bit surprised that this is part of the AS level interface that we allow access to that. But,
Don't you have to do that the internet address of the pipeline to put code there?
why do you need to do
Like, because
up to the point of that? And you still have to declare blocks. And you still have to declare blocks and then you can do that. But no one stops you from declaring a function and declaring this function as allocated to your function. Okay. Any further questions on this level of interrupt handling? We will do this in real life now very soon. Maybe more. Get actual experience